prevent oil leakage, control airflow cooling and prevent stray airflows into turbine cavities. A series of, for example, labyrinth seals allow a small flow of bleed air to wash the turbine disc to extract heat and, at the same time, pressurize the turbine rim seal, to prevent hot gases entering the inner part of the engine. Other types of seals are hydraulic, brush, carbon, etc. Small quantities of compressor bleed air are also used to cool the shaft, turbine shrouds, etc. Some air is also used to keep the temperature of the combustion chamber walls below critical. This is done using primary and secondary air holes which allow a thin layer of air to cover the inner walls of the chamber, preventing excessive heating. Exit temperature is dependent on the turbine upper temperature limit depending on the material. Reducing the temperature will also prevent thermal fatigue and hence failure. Accessories may also need their own cooling systems using air from the compressor or outside air. Air from compressor stages is also used for heating of the fan, airframe anti-icing and for cabin heat. Which stage is bled from depends on the atmospheric conditions at that altitude. Fuel system, edit. Apart from providing fuel to the engine, the fuel system is also used to control propeller speeds, compressor airflow and cool lubrication oil. Fuel is usually introduced by an atomized spray, the amount of which is controlled automatically depending on the rate of airflow. So the sequence of events for increasing thrust is, the throttle opens and fuel spray pressure is increased, increasing the amount of fuel being burned. This means that exhaust gases are hotter and so are ejected at higher acceleration, which means they exert higher forces and therefore increase the engine thrust directly. It also increases the energy extracted by the turbine, which drives the compressor even faster, and so there is an increase in air flowing into the engine as well. Obviously, it is the rate of the mass of the airflow that matters, since it is the change in momentum, mass x velocity, that produces the force. However, density varies with altitude and hence inflow of mass will also vary with altitude, temperature etc., which means that throttle values will vary according to all these parameters without changing them manually. This is why fuel flow is controlled automatically. Usually there are two systems, one to control the pressure and the other to control the flow. The inputs are usually from pressure and temperature probes from the intake and at various points through the engine. Also throttle inputs, engine speed etc. are required. These affect the high-pressure fuel pump. Hydromechanical unit, HMU, edit. Engine thrust has to be maintained or varied at the will of the pilot by varying the fuel flow. But it has to be done without exceeding any limitations which could damage the engine or cause a flame out. A combustible mixture has to be maintained in the combustion chambers to prevent lean or rich flame out. Complex hydromechanical units were used to implement these requirements before electronic engine controls were developed. The following explains some HMU functions for fuel control systems in the 1960s. The fuel flow depends on the area of a variable restriction in a fuel tube, a throttle valve which has its area adjusted by the pilot, and the pressure drop across it. The pressure drop has to be maintained by the HMU if the pilot's throttle valve is to control the fuel flow. The fuel must be reduced with altitude to maintain the same A/F ratio, as the lower ambient pressure means less weight of air entering the engine. Early engine controls used a barostat or barometric pressure control depending on the type of fuel pump, fixed or variable displacement. When the pilot wants more thrust, the rate of increase in fuel flow that comes with moving the thrust lever, throttle, must not be too great, but at the same time must be enough to accelerate the engine quickly without stalling the compressor. When reducing thrust, the rate at which the fuel decreases must not be too quick or a flame out will occur. At high engine speeds, overspeeding and over-temperaturing going beyond the maximum allowable, must be prevented to avoid turbine blade damage. An example of an HMU, although called a constant all-speed control, CASC, was the Rolls-Royce /Lucas fuel control used on the Rolls-Royce Spee. It performed all the above functions as well as maintaining the HP shaft speed, being the basic control parameter, selected by the pilot for most subsequent flight conditions. The LP shaft speed was prevented from exceeding its aerodynamic speed, N/SQRTT, limit which occurs at low inlet temperatures. The maximum pressure in the engine, which occurred on cold days, to preserve the fatigue life of the casings. The following describes a recent fuel control that used on a CFM International CFM 565B engine, installed on an Airbus A320, which has a FADEC controlling and computing all the functions previously done by an HMU. An HMU is still required because electrical actuators, torque motors or stepper motors, are needed to convert the digital signals from the FADEC into fuel flow changes. The HMU has to implement the following: the variable restriction, called the fuel metering valve FMV, and the pressure drop across it, by using a bypass valve between the high-pressure fuel pump and the FMV. The pressure drop is kept constant so the fuel flow to the fuel nozzle only depends on the FMV position. The pilot's thrust lever request for fuel is only one request that goes into the FADEC to position the FMV. Others, such as the HP rotor speed, will modify the pilot's request as necessary before sending a signal to the torque motor which sets the position of the FMV. The HMU also sends fuel hydraulic signals using FADEC-controlled individual torque motors to actuators for the variable stator vanes, low and high pressure turbine clearance control, high pressure compressor clearance control and a motor for the variable bleed valves. Propellant pump, edit. Propellant pumps are usually present to raise the propellant pressure above the pressure in the combustion chamber so that the fuel can be injected. Fuel pumps are usually driven by the main shaft, via gearing. Turbo pumps, edit. Main article, turbo pump. Turbo pumps are centrifugal pumps which are spun by gas turbines and are used to raise the propellant pressure above the pressure in the combustion chamber so that it can be injected and burnt. Turbo pumps are very commonly used with rockets, but ramjets and turbojets also have been known to use them. The drive gases for the turbo pump is usually generated in separate chambers with off-stoichiometric combustion, and the relatively small mass flow is dumped either through a special nozzle, or at a point in the main nozzle. Both cause a small reduction in performance. In some cases, notably the Space Shuttle main engine, staged combustion is used, and the pump gas exhaust is returned into the main chamber where the combustion is completed and essentially no loss of performance due to pumping losses then occurs. Ramjet turbo pumps use ram air expanding through a turbine. Engine starting system, edit. The fuel system as explained above is one of the two systems required for starting the engine. The other is the actual ignition of the air-forward/fuel mixture in the chamber. Usually, an auxiliary power unit is used to start the engines. It has a starter motor which has a high torque transmitted to the compressor unit. When the optimum speed is reached, i.e. the flow of gas through the turbine is sufficient, the turbines take over. There are a number of different starting methods such as electric, hydraulic, pneumatic, etc. The electric starter works with gears and clutch plate linking the motor and the engine. The clutch is used to disengage when optimum speed is achieved. This is usually done automatically. The electric supply is used to start the motor as well as for ignition. The voltage is usually built up slowly as starter gains speed. Some military aircraft need to be started quicker than the electric method permits, and hence they use other methods such as a cartridge turbine starter or cart starter. This is an impulse turbine impacted by burning gases from a cartridge, usually created by igniting a solid propellant similar to gunpowder. It is geared to rotate the engine and also connected to an automatic disconnect system, or overrunning clutch. The cartridge is set alight electrically and used to turn the starter's turbine. Another turbine starter system is almost exactly like a little engine. Again, the turbine is connected to the engine via gears. However, the turbine is turned by burning gases. Usually the fuel is isopropyl nitrate, or sometimes hydrazine, stored in a tank and sprayed into a combustion chamber. Again, it is ignited with a spark plug. Everything is electrically controlled, such as speed, etc. Most commercial aircraft and large military transport airplanes usually use what is called an auxiliary power unit, APU. It is normally a small gas turbine. Thus, one could say that using such an APU is using a small gas turbine to start a larger one. Low pressure, 4070 psi or 28480 kPa, high volume air from the compressor section of the APU is bled off through a system of pipes to the engines where it is directed into the starting system. This bleed air is directed into a mechanism to start the engine turning and begin pulling in air. The starter is usually an air turbine type, similar to the cartridge starter, but uses the APU's bleed air instead of the burning gases of the propellant cartridge. Most cart starters can also use APU air to turn them. When the rotating speed of the engine is sufficient to pull in enough air to support combustion, fuel is introduced and ignited. Once the engine ignites and reaches idle speed, the bleed air and ignition systems are shut off. The APUs on aircraft such as the Boeing 737 and Airbus A320 can be seen at the extreme rear of the aircraft. This is the typical location for an APU on most commercial airliners, although some may be within the wing root, Boeing 727, or the aft fuselage, DC-9/MD-80, as examples, and some military transports carry their APUs in one of the main landing gear pods, C-141. Some APUs are mounted on wheeled carts, so they can be towed and used on different aircraft. They are connected by a hose to the aircraft ducting, which includes a check valve to allow the APU air to flow into the aircraft, while not allowing the main engine's bleed air to exit through the duct. The APUs also provide enough power to keep the cabin lights, pressure and other systems on while the engines are off. The valves used to control the airflow are usually electrically controlled. They automatically close at a predetermined speed. As part of the starting sequence on some engines, fuel is combined with the supplied air and burned instead of using just air. This usually produces more power per unit weight. Usually an APU is started by its own electric starter motor, which is switched off at the proper speed automatically. When the main engine starts up and reaches the right conditions, this auxiliary unit is then switched off and disengaged slowly. Hydraulic pumps can also be used to start some engines through gears. The pumps are electrically controlled on the ground. A variation of this is the APU installed in a Boeing F/A-18 Hornet. It is started by a hydraulic motor, which itself receives energy stored in an accumulator. This accumulator is recharged after the right engine is started and develops hydraulic pressure, or by a hand pump in the right-hand main landing gear well. Ignition, edit. Usually there are two igniter plugs in different positions in the combustion system. A high voltage spark is used to ignite the gases. The voltage is stored up from a low voltage, usually 28 VDC, supply provided by the aircraft batteries. It builds up to the right value in the ignition exciters, similar to automotive ignition coils, and is then released as a high-energy spark. Depending on various conditions, such as flying through heavy rainfall, the igniter continues to provide sparks to prevent combustion from failing if the flame inside goes out. Of course, in the event that the flame does go out, there must be provision to relight. There is a limit of altitude and airspeed at which an engine can obtain a satisfactory relight. For example, the General Electric F404-400 uses one igniter for the combustor and one for the afterburner. The ignition system for the A/B incorporates an ultraviolet flame sensor to deactivate the igniter after light off on minimum fuel has been detected. Most modern ignition systems provide enough energy, 20-40 kV, to be a lethal hazard should a person be in contact with the electrical lead when the system is activated, so team communication is vital when working on these systems. A lubrication system, edit. A lubrication system serves to ensure lubrication of the bearings and gears and to maintain sufficiently cool temperatures, mostly by eliminating friction. The lubricant can also be utilized to cool other parts such as walls and other structural members directly via targeted oil flows. The lubrication system also transports wear particles from the insides of the engine and flushes them through a filter to keep the oil and oil-wetted components clean. The lubricant is isolated from the external parts of the engine through various sealing mechanisms, which also prevent dirt and other foreign objects from contaminating the oil and from reaching the bearings, gears, and other moving parts, and typically flows in a loop, is not intentionally consumed through engine usage. The lubricant must be able to flow easily at relatively low temperatures and not disintegrate or break down at very high temperatures. Usually the lubrication system has subsystems that deal individually with the lubrication supply system of an engine, scavenging, oil return system, and a breather, venting excess air from internal compartments. The pressure system components are typically include an oil tank and aerator, main oil pump, main oil filter forward/filter bypass valve, pressure regulating valve, PRV, oil cooler forward/bypass valve and tubing forward/jets. Usually the flow is from the tank to the pump inlet and PRV, pump to main oil filter or its bypass valve and oil cooler, then through some more filters to jets in the bearings. Using the PRV method of control means that the pressure of the feed oil must be below a critical value, usually controlled by other valves which can leak out excess oil back to tank if it exceeds the critical value. The valve opens at a certain pressure and oil is kept moving at a constant rate into the bearing chamber. If the engine power setting increases, the pressure within the bearing chamber also typically increases, which means the pressure difference between the lubricant feed and the chamber reduces, which could reduce flow rate of oil when it is needed even more. As a result, some PRVs can adjust their spring force values using this pressure change in the bearing chamber proportionally to keep the lubricant flow constant. Control system, edit. Main article, FADEC. Most jet engines are controlled digitally using full authority digital electronics control systems, however some systems use mechanical devices. See also, edit. 1 Index of aviation articles. 2 Advanced technology engine. References, edit.